Hey, Algebra 1, we're going to be talking about Lesson 1, Lesson 2, Lesson 3, and Lesson 4 in Saxon Math, Algebra 1. The first section, we're going to be talking about classifying real numbers. And when we classify real numbers, we kind of need to know the categories to classify them in. So what I want you to know, Algebra 1 students, is that complex numbers, all numbers are complex. We'll discuss that in more detail later. And the complex numbers are broken down into two categories, the real and the imaginary. Yes, there are imaginary numbers. Real numbers are the ones that we're used to. That's why I have all of this highlighted in yellow. So we're going to talk about real numbers, which are broken down into the rationals and irrationals. Irrational numbers are going to be numbers that you might remember, like the square root of 2 and the square root of 3 and pi and numbers of that order. So any radicals or any square roots or cube roots that do not simplify into a typical number that we're used to, a whole number, then we're going to call that irrational, because you're going to create a decimal that will go on but will not repeat. It'll go on forever and ever in a predictable or in a non-repeating way. Rational numbers, on the other hand, I like this word rational because it has the word ratio in it, and it reminds me that rational numbers can be written as a ratio or as a fraction. So any number that I can write as a fraction of two whole numbers, I'm good to go. Negative or positive whole numbers. So I can have 4 over 7, that's rational. 1,000 is a rational number. Negative 623, rational numbers. As long as I can write it as a ratio, right? We know 1,000 can be written as 1,000 over 1. Even the decimal, the repeating decimal point 33333 repeating, we know that can be written as 1 over 3. Therefore, that is a rational number. So lots of rational numbers. Those are the ones we hang out with the most. Irrational numbers happen from time to time. Now, when we're dealing with rational numbers, we have a subset called the integers. Integers, I like to refer to them as number line numbers. They're negative and positive whole numbers. So if you think of a typical number line, those are going to be your integers, all right? That's a -1, -2, so forth and so on. Whole numbers start with 0, and we start counting up. Whole numbers, whole number steps, 3, 4, and we'd write it in set notation as the text talks to us about, like this. The set of numbers starting at 0, 1, 2, 3, 4, and these 3 dots, ellipses, means that continues on. And finally, counting numbers, I like to think about them as kindergarten numbers. We don't really teach the little kids about 0. We try to teach them to count 1, 2, 3, 4. So natural numbers and whole numbers are very close, except for this one element in the set 0 that whole numbers have that natural numbers don't. Now that we've gotten that out of the way, we need to talk about what category each of these numbers belongs to, every category. And so if you look at 1/2, you know that it's a real number. It's what we've been used to. Is it rational or irrational? Hopefully by virtue of it being a fraction, you can see that it's rational. Is it an integer? No, because it's not a whole number, negative or positive. It's not whole, it's not natural, but it is real and it's a rational number. And so that would be the answer. So if you look at the answers there, you see that it's a rational number and it's a real number. Let's go ahead and take a look at this example 5. Since we can write 5 as a fraction, 5 over 1, we know that it is real, it is rational. It's also an integer, right? It's one of the negative or positive whole numbers. It's a whole number, and it is a counting number. So it fits all of the categories. The next one we're going to talk about is 3 times the square root of 2. And if you haven't thought about it, that square root of 2 is really important because it really indicates that we're dealing with a real number that is irrational. I cannot write a radical I would say the square root of a number that does not resolve to a whole number. I can't write it as a fraction. If it has to be a decimal, then that's all it's going to be. It's going to be irrational. And so that's a clue for us. So let's go ahead and write that down. There we go. So here in example 2, we're going to identify sets for the real world situation. So we're going to still think about those number values that we talked about, or those categories, but we're also going to see how it applies to real life. So the value of the bills in a person's wallet. Well, we know when we're dealing with dollar bills, at least in this country, there are no fractions. These are whole numbers. And so if we're dealing with whole number values of people's bills in their pocket, we can only have from 0 up to whatever number we have, right? Like we can only have 0, 1, 2, 3, 4, 5. And what numbers are those? Those are whole numbers. So this would be a whole number situation. Makes sense? Hopefully it does. Hopefully. The balance, oh, I guess I should just reveal the answer. All right, so there it is. So we're looking at whole numbers in this case. The balance of a checking account. So your checking account is interesting. You can have all kinds of money in there, decimals, fractions, all the things, right? In terms of like 50 cents in your checking account, that could be your balance. But also your balance could be negative. So if you have a checking account and you write a check that you do not have enough money to cover, your bank will definitely take that money out in the form of giving you a negative balance. So we're talking about negative numbers that are positive and negative and also fractions. So at first I thought integers, but since we're dealing with fractions, I also have to say, if you remember, let me scooch back up here. Irrational numbers are these guys. I really just want rational numbers, numbers that can be negative and positive and fractions. So that's what we have there. And finally, this last one, the circumference of a circle table with the diameter is a rational number. And so let's think about it. You've got a circle table, something like this, and the diameter is a rational number. And so what we know is that the circumference, that's this edge on the outside, that's the circumference, the length of that. The circumference is going to be equal to pi times the diameter. Now pi, as we mentioned before, is an irrational number. It is irrational. It is approximately 3.14, but it continues on and on and on. When I multiply that by d, which is a rational number, it won't change the fact that this is an irrational. So a rational times an irrational is still irrational. So what that means is that the circumference that we get would be an irrational number because that would describe the situation. All right. Hopefully that's a little bit of review and that wasn't too bad. Let's look at example 3. So here in example 3, we're going to be talking about sets and two different notations for sets. So the first one is the idea of intersection. And we use this upside down U shape, and the idea of union, which follows the U shape. So union is everything together, all of it together, and intersection is just what they have in common, or how they overlap. So for instance, if we were to refer to A in intersect B, right? Set A intersect B. The way I'd answer this is, what values are the same in both sets? So if I look at this set, I see that there's a 6 in both of these sets, and there's also a 12. And so the intersection of sets A and B would be a new set, and that set would be 6, 12. Okay, so intersection is the overlap, literally where they intersect. And so now we'll talk about A in union with B. Now, A in union with B is the set of all of it together. This should be a curly bracket here, is the set of all of it together. So we would include every element from both sets without writing the element twice. So we'd have 2, we'd have 3, we'd have 4, we'd have 6, we'd have 8, 9, 10, and 12. Notice that every element of both set A and both set B would be in set A union B without the repetition. Notice I didn't write 6 twice or 12 twice. All right, let's try the idea again. Here I have set A and set B, and I want to know what the intersection of those sets are. What's the intersection? What do they have in common? So I see these guys are odd, these guys are even, and in fact, they have nothing in common. There is no overlap here. And so what I do in a situation like this, my answer is going to be the empty set. The empty set is just a set with nothing in it. This is one way of writing the empty set. The other way is like this. So both of these are equivalent and both of these are the answer to A intersect B. So A union B in this situation is just going to collect all of those numbers. And so we are going to have 11, 12, 13, 14, 15, 16, 14, 15, 16, 17, all the way up to 18, because that would be all of the numbers present in both of those problems, in both of those sets. So example 4, we're going to be identifying a closed set under a given operation. And what that refers to is the idea that if an operation is performed on any of the elements of the set, and then the answer is therefore in the set, that means it's closed. So let's think about it. And so it says, determine whether each statement is true or false. Give a counter example for the false statement. So the set of whole numbers is closed under addition. So let's think about the set of whole numbers for a moment. If we were to take this set and take any two elements from this set and add them together, would we get another element of the set? And so you can just work on it and just grab two numbers. How about 2 and 3? When I add it, I get 5. Is 5 in that set? Yeah, it is. How about 4 and 17? When I add those two numbers together, I get 21, and 21 would be in that set. And you can kind of feel like the more you do this, that you know that this set is closed over or under addition, because I can't take any two numbers and add them, or any 3 or any 5 or any number of numbers in this set, add them together and not get yet another number that's in this set. I hope that made sense. All right, let's look at this one. The set of whole numbers is closed under subtraction. So I'm going to say, let me go back up and answer the question. This is true. And here's a couple of examples that not necessarily verify it, but support it in our mind, helps us to comprehend the idea. So this one is actually false, and we're going to talk about why. So if you take, again, the set of whole numbers and you choose two random numbers in that set, and so 4 and 7, let's say. If I have 4 and 7 and I subtract them, I get 3, and that seems good. But if I were to take those two numbers and switch them, 4 minus 7, hopefully you guys know that that's -3, and that's not in this set. And so that is our counterexample that proves that this statement is false, and indeed whole numbers are not, or the set of whole numbers is not closed under subtraction. So that brings us to our lesson practice and the other assignment that we talked about earlier, which is the additional written problems that are going to be more review. Definitely get all of the lesson practice done, please. But I'd also like you to consider, if you're checking your work, the assignment, you can look here. When I did a Google search for the answer and answer book for your text, I noticed that what we could find is, well, getting a text is one thing, but what we could find is the answers on Quizlet. And so let's see, if you go to Quizlet and you click on the edition with the camera on it, that's what the cover of your book looks like, you have access to all the answers in your text, not just the practice problems, the first initial practice, but also the other practice problems later on. So you may have to sign in, but I'll just show you a glance of what it looks like. You see that the answers for the warm-up, the lesson practice, and the practice are all here. So not just the lesson practice I showed you, but also the practice. So be sure that you work to get access to the answers when you're doing the homework, so you can be confident that you're doing it correctly. So you are responsible for checking your work because we do have access to it here. All right, so let's get back to the other lessons. So here we are with lesson 2, and we're going to be understanding variables and expressions. So a couple things that we should probably know. A variable is just a letter that, and sometimes another symbol, but just a letter that's used to represent a number. So if I were to give you something like this and say x plus 4 is equal to 7, if you think about it, you know that x has to equal 3. So here, 3 was hiding out under the disguise as X. And you literally could think of it that way. You can think about these variables, these letters that represent numbers, is just kind of like an overcoat for a number. It's a hiding space. And yes, X won't always be 3. It will change, and that's why we get the term variable. The value for these letters or symbols varies. So here we're going to identify some variables and constants, and so I like talking about this. So in this expression, we have 6 minus 3x, and we need to identify the constants, and I'll highlight the constant here in yellow, and the variable. Let's highlight that in red. And so if we're going to do constants, a constant is something that will always be the same. So a constant, as opposed to a variable, is just a number hanging out by itself. So 7 is a constant. 9 is a constant. -3, -1/2, 0.721. Anytime we have a number hanging out by itself, not hanging next to a variable, but hanging out all alone by itself, we know that that is a constant. So if I'm going to identify the constants, I'm going to say that 6 is a constant. 3 isn't, because it is hanging out next to a variable. And so that would not be a constant. That has another name that we'll talk about. It's a coefficient. And so I'm highlighting X as the variable and 6 as the constant. Let's look over here. In this next example, we see that we have a couple of variables. Here, W and Z are being multiplied together. Those are 2 variables. Y, also a variable. In this expression, there are no constants. There are no numbers that are chilling by themselves and without like a variable next to it. Here in example 2, we're going to be talking about factors and coefficients. Factors are numbers that multiply to give me another number. So for instance, if I have the number 48, I can say 2 factors of 48 would be 6 and 8. So these are factors. And coefficient is a special number. So a coefficient is a number that is being multiplied next to or right by variables. So 2 here is the coefficient. Let's go ahead and list the factors and coefficients of each of these expressions. So here the factors are 7, V, and W, because each of them are being multiplied together to give us this number 7VW. Over here, the coefficient is the real number that is multiplying whatever variables we have, and so that's going to be 7. Here, our factors are -5, R, S, and T. Our coefficient is -5. This looks a little tricky, but we do have things that are being multiplied together, or we can look at this problem as if something's being multiplied together, y and 1/3. If y and 1/3 are being multiplied together, 1/3 is the real number, and so 1/3 is the coefficient. Here, C and D are both factors. However, it looks like we don't have a coefficient. Technically, we do. That coefficient is 1. Anytime you have a variable hanging out by itself, we know that really we could say that that's 1 times that variable. So for instance, you remember I said that 2x was an example where 2 is the coefficient. Well, if I have y, technically that's the same as having 1y. So y is the same as having 1y. I can say that the coefficient here is going to be 1. Make sense? So simply because there's no number here, 1 times CD is the same as CD, therefore 1 is the coefficient. So this is kind of cool when we talk about terms. When you have a math expression, terms are chunks of numbers or numbers that are strung together by plus signs and minus signs. So for instance, if I had 4 plus 2x minus 7yz plus, let's say, pi, just trying to make it fancy for you. If I had these things strung together with the plus sign, the minus sign, and the plus sign, then all of these are terms of this expression. So how many terms do I have? Let me highlight it. I've got 1, 2, 3, and 4 terms. I've got 4 terms here. So identify the terms in each expression. We should be able to highlight each of the terms in the expression that we have here. So let's go ahead and check it out. Let me see if we can use a different color. So let's use this yellow. Here's one term. Remember, terms are strung together by addition or subtraction signs. Here's another one. And all of this, yes, chunked together, is another one. Terms are never separated by multiplication. In fact, multiplication and division chunk them together. So we've got 3 terms there. Here's another term. Here's another one. This whole thing is a term, and this is a term. This is a 4-term expression. So we have example 4, and this is our final example before our lesson practice, which you should do. All right, so this application is telecommunications. The local telephone uses the expression below to determine monthly charges for individual customers. Fine. So we've got 0.1 times M, whatever that is. Maybe it's the month or the number of calls made in the month, who knows, plus 4.95. How many terms are in the expression? Well, that part we remember, we're going to count everything that is separated by a plus sign or minus sign. So this first one, we have 2 terms. Identify the constants. Well, let's look at the value again. You've got 0.1 M plus 4.95. If you remember, constants are numbers that are always going to be the same and that will never change. So our constant here is 4.95. Our variable, on the other hand, would be M. Our variable would be this M value here, because I'm not sure what M is, and it can change. It varies because it's not a definite thing. It's not a constant. So that's all we have for lesson 2. Be sure to do the lesson practice and the other practice so that you are ready and available to learn. And so know that the answer choices or the answers can be checked on Quizlet. Here we are at chapter or lesson 3. We're going to be talking about simplifying expressions using the product property of exponents. All right. So the product property we're going to talk about in a minute. If you remember exponents, they're the little tiny number, the power that hangs out next to a number, and it tells me how many times I'm multiplying it together. So 5 to the first power is just 5. 5 to the second power is 5 times 5, or 25. 5 to the third is multiplying 5 3 times, and you get 125, and 5 to the fourth is 5 times 5 times 5 times 5. All right, so the first thing we're going to do is simplify these expressions by actually doing them. So here we would be multiplying 7 times 7 times 7, and we get, I think, 343, if I'm not mistaken. I think I memorized that a long time ago. So we're talking about 49 times 7. I'm just checking it. 7, 9, 63. 7 times 4, 28, 29, 30, 31, 32, 33, 34. Yeah, so we get that value. And I would suggest, I did that knowing that you probably didn't memorize it. And that makes sense. Who does that? But memorize some of these. They're going to come up so often that you want to do that. All right, so over here we have 0.3 to the fourth power. I know that 3 to the fourth power is equal to 81, because that's like 3 times 3 times 3 times 3, and 3 times 3 is 9, and 3 times 3 is 9, and that's going to give me 81, right? So this is a thought bubble in the back of my mind. So I know if I'm multiplying these numbers together, 0.3 times 0.3 times 0.3 times 0.3, it's going to be a lot like multiplying 3 times 3 times 3 times 3 together, because 81 is going to be a part of it, but I've got to count the decimals. 1, 2, 3, 4. And so I'm going to have 81, but I'm going to move that decimal over 4 times. So that's 1, 2, 3, and 4. Put my zeros in here. 1, 2, 3, and 4. And then so I'm going to get those decimals out of there too, because those are looking crazy. And then, I'm losing my answer. So then I get this number, or 0.0081, or 81 10,000ths, if I wanted to write it like that. Here we're going to write 1 over 2, and we're going to write that over and over again 5 times so we can figure out what 1/2 to the 5th power is. If you notice, when I multiply these fractions, the numerator is just going to be 1 because I'm multiplying 1 times 1 times 1. The denominator, however, is going to be 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power, which you might remember is 32. Okay? Am I telling the truth? Yeah, I am. 2 times 2 is 4, times 2 is 8, times 2 is 16. Yeah, 32. All right, good. So 10 to the 3rd power is our final part of this example. And so we know that's multiplying 10 3 times. But the cool thing is, when you multiply 10 like this, you can multiply the ones and just add the zeros in like that. So notice that this 3 actually predicted the number of zeros, and that's something you could use to help you later on. All right, so we're looking at the product property of exponents, and so the product property is this. It says if you have x to the m power times x to the n power, you get x to the m plus n. And I know you're like, what? Let's think about it in terms of real terms numbers. Okay, so if I have 3 squared times 3 to the, let's say, 3rd power, that would be equal to 3 to some power. Let's think about what that means. If I were to calculate 3 squared, not calculate, but write it out in expanded form, I would get 3 times 3. And then if I were to expand 3 to the 3rd power, I would get 3 3s being multiplied over here, right? Hopefully this is like, yeah, sure, whatever. So these two are the same. This is the same. Let's get a new color for that. This is the same as that. So I'm just rewriting it in the expanded form. Now the next thing you know, you can see that clearly. I'm going to end up with 3 times 3 times 3 times 3 times 3, or 5 3s. And 5 3s would put a 5 up here. So what does this have to do with this cryptic message up here? Well, it's everything. If I'm multiplying two numbers with the same base, x and x, and they have an exponent, doesn't matter if they're the same or different, I'm going to take that same base and simply add the exponents. I am adding m and n in order to get m plus n. I am adding 2 and 3 in order to get 5 here. So that would save me a lot of writing out things and counting lots of numbers if I get to understand this property, memorize it, and apply it. So if I apply that property, it says as long as I'm multiplying things with the same base, I can add the exponents. So this is x to the 5th. I don't know if you guys can see this well. I am going to try to rewrite it. I've got x to the 5th times x to the 7th times x to the 2nd. And that rule says I can add all these exponents together because this is 5x's, 7x's, and then 2x's all together. I'd have the sum of the exponents as the number of x's that I have. So 5 plus 7 is 12 plus another 2 is 14. So this gets to be x to the 14th power. And so that's what they have here. I didn't realize that the answer was there. I'm sitting up here singing my heart out and the answer's right here. Well, let's try this one. I was successful in erasing the answer. Let's go ahead. M to the 3rd power times m to the 2nd times m to the 4th times m to the 6th times n to the 7th. These are n's, my bad. So I'm going to rewrite that problem real quick. So it would be nice if we could just take everything and add it all together, but we have to be really circumspect, really looking around, checking out what's going on. We see that there are 3 of these terms that have the same m base and 2 that have the n base. And so they can't be joined together, but I can certainly join these 3 together. M to the 3rd, m to the 2nd times m to the 4th, all of that comes together to give me, can you see? M to the 9th, because there are 9 m's here. 3 and 2 is going to give me 5 plus 4 is 9. And then over here, these n's are going to come together. Since I've got 6 n's here and 7 n's here, altogether I have 13 n's. So the simplified version of this is m to the 9th times n to the 13th. And I'm going to stop there before I go on to my next example, example 3. Okay, this is going to seem strange, but example 3 is talking about something that I really have never heard of, but let's go with it. The fastest supercomputer in 2006 performance topped out at about 1 pflops. I don't know what that is, but we're going to learn and calculate even though we're not sure what it is. 1 pflop is equal to about 10 to the 3rd tflops. So I'm going to write that bit down. P-flops, one of those, one P-flops, I don't know what that is. Should be an S there. Okay, whatever. One P-flops, you see I'm struggling, is equal to 10 to the third T-flops. T-flops. Okay, got it. And now the other bit of information we need to keep in mind is that each of these T-flops, is equal to 10 to the 12 flops. All right. There we go. So with that in mind, we want to know how many flops are in one P-flops. How many flops are in one P-flops? Hopefully you can see that since one P-flop has 10 to the third T-flops, we're going to need to multiply, because for each of these T-flops, there's 10 to the 12 flops. Ooh, I think you might have to rewind that and listen to me say it again. It was truthful, but it sounded crazy even to my ears. So one P-flops is equal to 10 to the third times 10 to the 12. 10 to the third is the number of T-flops, and 10 to the 12th is the number of flops in a T-flop. Whew, say that again. All right, so that is going to be equal to 10 to the third times 10 to the 12. Remember, we're multiplying two numbers with the same base. We're going to add the exponents. We're going to end up with 10 to the 15th. So that's how many flops, 10 to the 15th flops, are in P-flops. Whew. Here's our lesson practice. Do it all, do it all. You get to have fun with E-flops and G-flops. And you get to do some of that work. Don't forget your answers are on Quizlet, and you can check, and you should check. All right, let's go ahead and get on to the last lesson. The final thing we're going to talk about in this example is going to be using order of operations. We remember what order of operations are, right? Order of operations refers to the order in which we do mathematical operations. And so we start off with, sometimes we use the mnemonic device PEMDAS, or kind of, what would that be, like an acronym? So what we want us to remember is that first we're going to do everything in the parentheses. That's what the P stands for. So that's the first thing, do what's in the parentheses. So in addition to parentheses, we mean brackets, parentheses. We can talk about brackets. We can do what's in the bracket first, do what's in the parentheses. Even any other kind of grouping symbol, we want to do what's there first. The next thing we want to deal with is the exponents. Exponents are really important, and they affect particular numbers in our expression. We want to make sure and handle that. Next, we want to do multiplication, and I want you to know that multiplication and division are actually equal. And so we say multiplication and division will be done at the same time, but left to right. Okay, so if you have an expression where there's multiplication and division, you want to do them left to right, all at the same time. Not letting one supersede the other. And then the final grouping that we're going to do together is to deal with addition and subtraction. And those are definitely equivalent. You're just going to go from left to right with those operations. Addition and subtraction is superseded by multiplication and division. Multiplication and division is superseded by exponents, and exponents is superseded by parentheses, which when I say that, I just mean the one that is on top is more important. All right, so let's look at our example here. Example 1 says that we're going to simplify expressions with parentheses. And so remember, if we're doing order of operations, we need to do what's in the parentheses first. So I'm going to go from left to right looking at the parentheses. 10 times 3 is 30. Look at how I just wrote the plus 7 down. And then I'm going to deal with what's in the parentheses here. 5 plus 4 is 9. And I rewrote everything just dealing with one thing, which was what's in the parentheses. The next thing I'm going to do, I'm going to rewrite this again. I'm going to consider the rest of our order of operations. And we don't have any exponents, so I don't have to deal with that. But we do have multiplication and division. So here's the thing. Some students will run ahead and get 30 plus 7 is 37 and multiply that by 9. But notice, if we go by the order of operations, we know that multiplication is more important. We're going to multiply that 7 times 9 and get 63. And then we're going to add to that 30. And our final answer there is 93. All right. So order of operations is important in order to get consistent answers and in order to do our work correctly. So in example 2, we've got a couple of expressions that we're going to work on, and I left part of the answer here. Write the expression, then use the order of operations to simplify, which is really more of a plan. Let's try it. So we're going to start off by taking a look at everything that we have involved here. We have a lot of stuff going on. First thing I'm looking at, remember we've got this that we're dealing with. So are there any parentheses? Yes, that 3 is in parentheses, but there's really nothing to do there. But what I do see is that we have exponents. And so I'm going to go from left to right dealing with my exponents. So 4 to the 3rd power is going to give me 64. I'm going to just rewrite everything else except when I come to the next exponent. So this is 3 to the 2nd power, which is 9. Notice I just rewrote everything with exponents and I simplified only that. This 2 only belongs to the 3 and this 3 only belongs to the 4. So that's the only thing that is affected when I'm raising those things to those powers. Next thing I'm going to do is go around and see if there's any multiplication or division, and there is. Right here and right here. I take care of it from left to right. Notice I'm rewriting my 64 again. 9 divided by 3 is 3. And then I'm going to do 2 times 9, which is 18. Finally, I'm going to do addition and subtraction from left to right. So 64 plus 3 is 67. And then I'm going to subtract 18. And that's going to give me 49. Check my math. Sometimes I'm wrong, but I think that one was okay. All right. Over here, we have a really nice problem that illustrates something that is not super clear all the time. Whenever you have a fraction bar automatically kind of puts a parentheses or separates two parts of your problem. So in a way, you can think of this as one part, this is the other part, and then you can deal with everything last. So when you have a fraction bar, then you want to think about the top as one entity to deal with, the bottom as another entity, and then finally you can divide. So if we're thinking that way, let's look at what's happening in parentheses. We need to do what's in the parentheses first. In the parentheses, we've got multiplication and subtraction. So the first thing we're going to do is multiply. So we get 6 minus 2. Raise that to the 2nd power, all of that over 2. Again, I'm still simplifying this. 6 minus 2 is 4, so I get 4 to the 2nd power over 2. I'm going to deal with my exponents, which is going to give me 16 over 2, and finally I can multiply or divide, and in this case, we're going to get 8. Let's see what else we have in example 3. In example 3, we're going to calculate a value, but we're also going to use less than, greater than, or equal to show the relationship between both of these expressions. So if I come on this side, I'm going to use my skills. 1.5 plus 3 needs to be done first because that's in parentheses. I get 4.5. And notice I'm just writing everything exactly as it is before. The next thing I'm going to do is I'm going to take that and I'm going to deal with the exponent. And the exponent is going to give me 27 because that's 3 to the 3rd power. And now I'm going to go from left to right doing division. 4.5 divided by 9. I could do this. I'm knowing that 9 if split in half is 4.5. So I know that this whole thing is going to be 1.5. This thing divided by 9, 4.5 divided by 9 will be, I said 1.5, will just be 0.5 rather. It's going to be half. And so I get a half plus 27. And finally, if I add that together, I get 27.5. Remember, every example problem that I'm doing comes directly from your text. So if I'm not sounding great, or if you want like another reference, you can also read your textbook, which totally makes sense. So I'm getting 27.5. Let's go ahead and take a look at this. Over here, we have parentheses that come across on the numerator. So I'm going to add 18 plus 8, and I get 26. all of that over 2 minus 8 divided by 4. So again, I'm going to do division first, and then I'm going to deal with addition and subtraction. So there's no multiplication, but here's division and here's division. Let's deal with that. We get 13 minus 8 divided by 4 is 2. So 13 minus 2 is going to become 11. So now I'm comparing 27.5 to 11. And I'm hoping you could look at this and say clearly 27.5 is greater. And that's how we do that problem. Our final problem is this application comparing crop circles to a soccer field. A crop circle in a wheat field has a diameter of 100 yards. Its area is 3.14 times 100 over 2 quantity squared yards. A World Cup soccer field is 70 yards by 110 yards. Its area is 70 times 110 square yards. How much larger is the crop circle than the soccer field? So what we need to do is find the area of both. We need to find the area of the soccer field and the area of the crop circle. The area of the soccer field is pretty easy to calculate. It's rectangular, so we're going to multiply 7 times 110. The area of the crop circle, since it's a circle, it's going to require us to remember that a circle's area is found by doing pi r squared. So we're going to calculate that by looking over and seeing that the soccer field is 70 yards. No, not the soccer field. Sorry, that the diameter of the crop circle is 100 yards. And so if the diameter is 100, that means the radius is 50. So our answer is going to be pi times 50 quantity squared. 50 squared is going to be 2,500 pi. And so when I actually get an approximate value here, when I multiply these guys together, I get 7,700 for the area of the soccer field and 7,853.98 for the area of the crop circle. And so in this way, by calculating carefully, using my exponents first and going through, I get two values that's going to give me a good idea that the crop circle is larger, and the amount larger it is just going to be a subtraction problem, where I'm going to subtract 7,700 from this guy, which is going to give me, I'm sorry for being lazy, I'm just going to write it down. The difference is going to be 153.98, 153.98 square yards. That's going to be the difference. All right, I hope that made sense. Of course, you know we got lesson practice and then the other practice. Get it done. Get all of it done. Check your answers in Quizlet. I look forward to talking to you soon. Take care, sweetie. Bye-bye.